Hi, I'm Stephen Neshiba, here to help you out with electron configurations. There's a number of words that are going to be important in this. Aufbau, PEP, which stands for the Pauli exclusion principle. Subshell degeneracy. Subshell degeneracy the word degeneracy refers to a set of things that have the same energy. And Hund, that's talking about Hund's rule. So I'll get to all those. What I've kind of started off with here is a potential energy diagram. This is our old friend the Coulomb potential being drawn here as a function of D, which is sort of generically the distance between a nucleus and an electron. And here I've indicated the shells, the first shell, second shell, third shell. Now, when we look at the periodic table, well, what you'll see is that the top row of the periodic table pertains to n equals 1. The second row of the periodic table pertains to n equals 2, and so forth. So that's how I'm going to be working at here. Another pretty key idea here is that all these different shells have, I've sort of expanded the energy levels associated with them. Here's just the 1s orbital that belongs to the first shell. Not much more to say about that, but for the second shell, there's a 2s orbital and 3 2p orbitals, and what you can see is that their energies are not quite the same. The s energy is a little bit lower in energy than the 2p, and then we have a similar sequence for the third shell. So let's just get started here then. I'm going to use Aufbau. Aufbau says start adding electrons at the lowest possible place. Hydrogen has 1 electron, so I'm going to draw in 1 electron just like that. That indicates an electron in a 1s orbital, and the way we notate that is we say 1s with 1 electron. The brackets mean electron configuration of the atom that's indicated in there. We go to the next atom, that's helium. Helium has 2 electrons. To use Aufbau, I need to put it in the lowest orbital, and that's fine. But I'm going to now use PEP, which says if you have 2 electrons in the same orbital, they have to be spin paired. Okay, that means opposite spins. That's fine. I would write that as 1s with 2 electrons in it. So now we have a filled first shell. And obviously, when we start to go to the next element up, which is lithium, 3 electrons, we're starting to put some electrons into the second shell. And this is a notational convenience that I'm going to do here, because all the electrons that get put up here will sort of be built on top of a core of the first shell. Then that's notated just like this. Lithium has the same electron configuration with helium, but more electrons put on top of that. So which electrons are put on top of that? Well, if I'm going to use go for the next energy level up, I put it right here. Now you might ask, why didn't I put a third one in here? And the answer to that is once again the Pauli exclusion principle that says once you have 2 electrons spin paired in 1 orbital, that's all that can go there. All right, so I have a filled first shell, that's indicated by that, and then obviously I would need to say 2s superscript 1 to indicate that. All right. How about the next orbital? Well, or the next atom, that's beryllium, has 4 electrons. I'm going to put it just like that. We could say that's helium followed by 2s2, and so on. Now, I haven't drawn it here, but the next atom in the list is boron, okay? And I need to put that up there. The following atom on the periodic table is, we would have to decide now, where does that electron go? And next thing I'm going to invoke here is subshell degeneracy. This is all the second shell, that's true. The 3 orbitals associated with p orbitals, that's called a subshell. It's called a p subshell. And they all have the same energy, which means that there is subshell degeneracy. And when there is subshell degeneracy, then you have to be a little bit careful about where you put the next electron. I need to put 1 more electron in. Turns out you don't pair them up. You just put them right next door with the same direction of the arrow, and I have just invoked what's called Hund's rule. Okay, so we go to the next atom in the periodic table. There we go. Now I've got a few more atoms in the periodic table in the second row. After I've put one electron in half of these, then I start to double them up, okay? And by now I have 10 electrons. 10 electrons is the electron configuration for neon, And I would say, oh, well, that's the same as helium. That's this core electrons and all these valence electrons, which would be 2s2, 2p6. Okay? Well, we have one more shell to work on. So the next shell is the third shell. And I'm going to say, well, that's a filled shell, so I may as well just, when I'm talking about sodium, I'm just going to say, okay, we're going to start building on the electron configuration of neon up to here. Where's the next electron going to go? Obviously, it's going to go there. So the electron configuration of sodium is that of neon followed by a 3s1. After that, the pattern goes the same. Next electron, next electron, next electron, and so on. You keep on going until we get all the way up to argon. So the electron configuration of argon, which is a filled or nearly filled third shell, that's the same as neon, followed by 3s2, 3p6. And that covers the electron configurations of the first 3 rows of the periodic table.